going to take a look at problem 7.26. This is a nozzle, analysis of a flow of a fluid in a nozzle. And the nozzle has where the gas is coming in, or the fluid is coming in, has a diameter of 5 centimeters. And then where it exits, it has a diameter of 3.5 centimeters. Okay. Now it has a defined volume flow rate. And this one, it is a gas. Defines it as a gas. Okay. Okay. As previous, what are we looking for? Looking for delta V. And I just started by writing down what's given in the problem. So you're given the input to the nozzle has a diameter of 5 centimeters, and we assume it's circular. And the output of the nozzle has a diameter of 3.5 centimeters. And then we're given a volume flow rate. Okay. Now, I wrote it down here. It's volume flow rate. I said it's volume flow rate in, and then said it's equal to volume flow rate out is equal to essentially just the volume flow rate, right? So it's constant all the way through. All right. And so to make that assumption, we can actually take a step back and look at what's in the textbook. We can look at this equation starting with 7.24. And what this is essentially mass flow rate coming in is equal to the mass flow rate going out. Okay. Now, this is independent of whether or not you can compress the gas, essentially increase its pressure, or if the fluid is compressible or not compressible. So like if it's a liquid or if it's a gas. That's in general what you can say. Now, if it's incompressible, these densities are the same. So whatever density of the incoming fluid is going to be equal to the same density when it leaves. Okay? Leaves the system. Or in this case, what we're looking at is a nozzle. So if that's true, then you can just say the volume flow rates of coming in is going to equal to the volume flow rate going out. All right? Now, in this case, it says it's a gas. So it actually could be compressible. But there's one little note the author puts here, and basic idea here is that if the velocities are below 100 meters per second, you can essentially assume that it's incompressible, okay? Or at least when it's going through a nozzle, right? So this is analysis of a nozzle, or a diffuser, which is just the inverse of a nozzle. Okay, so we can actually go and apply this equation, since in our case, what we'll find is going to be below this, right? So, or at least it'll be within this range. But we can go ahead and determine that just from finding our velocity from V1. Okay. So that'll be the approach. The approach is first is to use this idea that volume flow rate equals cross-sectional area times its velocity. Okay, and that'll be the formula. Okay. So just taking a step back here and looking at the formula that was used, here's the governing equations. So volume flow rate equals velocity times cross-sectional area. And then the last thing we're looking for, the change in velocity, of course, is just V2, velocity going out, minus V1, whatever is coming in, okay? I didn't actually draw the velocities on here, but it's the velocity of the fluid coming in is V1, and velocity of the fluid leaving is V2. Okay. All right, and these are the cross-sectional areas. Okay, so first thing is we can find the velocity for V1. All right, velocity of V1 is 51 meters per second. All right, velocity and then you just put, here's the cross-sectional area. Make sure it's the radius, right? They give you the diameter. I just did it in half, which is the radius, which is 2.5 times 10 to the minus 2 squared times pi. Okay, so here's the velocity coming in. Here's the velocity going out. Okay, the velocity is 104 meters per second. Now, this comes out to be about 100 meters per second, but There's no other additional information for us, so we can make the assumption essentially that it's incompressible, or at least we're treating it as being incompressible. Okay? I didn't put that assumption in here, but it's one thing we should say. All right, then of course at the end it's simply just, delta V equals V2 minus V1, 104 meters per second minus 51 meters per second, 53 meters per second. So in order for us to solve this problem, we really need to say that it's incompressible or use that approximation. Although the author said it was 100 meters per second, in general, you could say that if it's less than the speed of sound, which is like 343 meters per second, you can actually use this estimate. Okay, and also, for us to be able to solve it, at least in the textbook, we are not giving any other information. So we really need to make that assumption in order for us to go through and solve this one. Okay, so we make the assumption because the velocity is relatively low, at least compared to the speed of sound, is that, which is 343 meters per second, is that we're basically treating this as if the fluid is not compressible. Okay? And any problem, if I ask you on like the final, I would make sure that, give you enough information to tell you that it's incompressible, or if it is, or it's not. Okay? So that's it for that problem.